you're saying that matter energy is going to affect space-time, right? What would you expect that the effect should be? We like that to space-time, matter energy. Space-time is affected by matter energy. What will it do? Will it change the color? And I don't mean in the physics sense. I mean, what could it do? If you had to come up with a theory, what would you say? So, suggestions like, how can you affect space-time? Any suggestions?
Curving or something.
Okay, is that something you just made up, or you might have heard something?
Well, no, I've heard something.
Okay.
The bowling ball.
Anybody else? Obviously, you may have heard something, but I'm just trying to kind of help you discover it, so to speak. What sounds reasonable? Is there anything, or I mean, it's not a simple question, obviously. Now, is it a ridiculous thing to even suggest that space-time is affected? Well, what happened is, mathematically, for example, in the previous millennium, in the century before last, I don't know, the 1870s or whenever it was, there were mathematicians who were studying the properties of mathematical spaces. And they found certain very intriguing things. Although the ancient Greeks, who came up with brilliant ideas of geometry and so on, said that it's necessarily the case that parallel lines never meet and a triangle has 180 degrees inside, etc., they found that you can construct mathematical systems which are self-consistent mathematically and logically, in which those things are not true. And those were kind of like, you would call it like curved surfaces or whatever, and I'll get into that a little bit more. It turns out that there's no logical reason that that can't be true also about space. Now, I'm not talking about space-time yet, but space. And Riemann, one of the great mathematicians, was looking into these kind of things, started looking around saying, well, let me see if there are any of these warpings due to something or other in space. And he tried to measure it, he couldn't find anything. And in fact, even from the general theory of relativity, we know that such an effect would be very, very tiny, minuscule, anywhere that you would look, not close to a black hole or something like that. So he didn't find it. Now, what would you expect as a manifestation of such a warping of space, let's say? For example, parallel lines would diverge, 180 degrees would not be the sum of the angles. You would have a radius of a circle. You wouldn't find pi, you would find some other number. Maybe it would vary, it'd be like a field. You would find here, you would find pi is equal to 3, here pi is 4, here pi is 2.7, right? It would always be the same number. All right? Those are the kind of things that you would expect to see in space warping. And what about time? What is a time warp? We've all seen science fiction probably. It's not that, right? Although those things might exist. What would you expect? How would you detect the warping of time? What does it mean? How would you measure it?
Well, like a second would be a second.
A second would be?
Like a second would be longer or shorter.
Okay. How would you measure that? I mean, maybe if everything is moving faster, so to speak, then nobody will know the difference that anything is not moving in sync with it, right? All right, in special relativity, you do have those kind of effects, time dilation. So that's a suggestion. You might have the same kind of effects that you have with time dilation in special relativity. You might have in general relativity, not as a result of motion, but as a result of mass energy. Mass energy affecting space-time, particularly time, causing differences in like the rate of time, which is not a sensible terminology, but you know what I mean. Okay, and in fact, it does occur.